Thank you, Alexei, for introduction. This is joint work with Sysloid. In this talk, I present a quantum algorithm that I call it universal quantum emulator. Let me start by explaining what do I mean by an emulator. So an emulator is a machine that mimics the behavior of another system without knowing what's going on inside that system. So it's just look at the input and output samples of the system and try to mimic the same kind of input-output relation. So this should be distinguished from a simulator, which knows what's going on inside the system and basically simulate the same dynamical equations to produce the same kind of input-output relation. In the quantum setting, we can formalize the problem in the following way. I assume there is a physical process, which is described by an unknown unitary U. I don't have any prior information about this unitary U, but I'm given multiple copies of sample input states of this unitary and their corresponding output states. And the goal is to use these given copies to emulate the action of U on a new given state psi. So you give me one copy of psi, and I return a state U psi. So to be more specific, here states phi in K and phi out K are the sample input states and the corresponding output states. So here K goes from 1 to capital K, and I'm assuming that I'm given multiple copies of each of these states. For example, you're given 10 copies of each of these states. And again, the goal is that you're given one copy of psi and transform psi to U psi. Obviously, this is possible only if psi is the subspace spanned by this input states, because otherwise in the orthogonal subspace you don't have any information about how U is defined or how it acts, so you can't emulate the action of U. Good. So one trivial strategy for solving this problem is to use tomography. Well, if you are given multiple copies of each state, then you can start performing measurements, and you can find an approximate classical description of each of these states. And then by solving a set of linear equations, you can find a unitary that relates the output states to input states, and then you can try to implement that unitary with a circuit. But you can easily imagine that if the space is large, in a large Hilbert space, this won't be practical. This will be a very inefficient method. In particular, the runtime for this approach will be capital D times Z, where capital D is the dimension of the entire Hilbert space, and this lowercase d is the dimension of this relevant subspace, which is spanned by my sample input states. Okay, so I call it H in, and its dimension is D. This is the dimension of this subspace spanned by the sample input states. So the runtime will be D times D, and the sample complexity will also be D times D. Here by sample complexity, I mean the total number of copies that you need to emulate the action of the unitary with a certain desired error. On the other hand, in the algorithm that I introduced in this talk, universal quantum emulator, the runtime is log D times logarithmic in the dimension of this entire Hilbert space and polynomial in the dimension of this relevant subspace. And the sample complexity is completely independent of the dimension of the Hilbert space, actually. It's just polynomial in the dimension of this relevant subspace. So you see that if the dimension of this relevant subspace is finite or is logarithmic in the dimension of the entire Hilbert space, this is an exponential improvement in over this naive method. Okay, so in the rest of my talk, I'm just going to talk about this algorithm and explain how it works. But before that, I need to tell you about the necessary condition for the possibility of emulation. Let's think about this question, when emulation is possible at all. Think about a simple example. Suppose my system is a qubit, a two-dimensional Hilbert space, and suppose the unknown unitary is a rotation around Z. So here, theta is an unknown angle. It's a rotation around Z. Now, if in this case, if the sample input states were chosen to be states 0 and 1, then because both of these states are invariant on the rotation around Z, by looking to the output of the unitary, you can't obtain any information about this unknown angle theta. Okay? So in this case, emulation is impossible. It's impossible using tomography or any other quantum or any other possible algorithm. So and you can see in this case, basically, it's easy to understand what's the issue. Because the states and 0 and 1 are orthogonal, basically there are unitaries which leave both of them invariant. And in this simple case, you can see that if you choose any pair of non-orthogonal distinct pure state, then you can basically get rid of this issue. So you can basically emulate the action of unitary by looking to the output states. But I need to formalize this more generally. And the general condition can be found easily. So let's remember again, H in is the subspace spanned by the sample input states. And then you can show that having copies of the sample input states and their corresponding output states, we can uniquely determine the action of U on states in the subspace H, in the subspace H in, if and only if this condition is satisfied. The algebra generated by the projectors to this input states should be the full matrix algebra on H in, on this input subspace. And by algebra, I mean just polynomials which are formed from these projectors. And the claim is that this condition is the necessary and sufficient condition. And it's easy to check this condition. And you can see in this particular example that I presented above, the algebra will be just the set of polynomials that are formed in this way will be all diagonal in the diagonal matrices in the 0, 1 basis. So basically, you cannot get off diagonal terms. So, and that's why basically that set of inputs do not work for emulation. So in the rest of the talk, I'm going to assume that this condition is satisfied. And actually, it turns out that this condition appears again in a very interesting way. Good. Another thing that I need to introduce before going through the algorithm is the notion of this control reflection. It's a notation that I introduced here. So here, A is a control qubit, and R in K is a reflection with respect to input state K, or R out K is a reflection with respect to output state K. So this is, if the first control, if the qubit is in a state 0, then the gate acts like identity. And if the control qubit is in a state 1, then it applies this unitary, e to the pi I pi phi k, which is basically a reflection with respect to a state phi k. Now, I'm going to, in the circuit that I'm going to present next, I'm going to use this unitaries. But obviously, I don't have these unitaries. But the point is, given the sample states that are given, the copies of these sample states that are given, I can approximately simulate this unitary. So this uses a previous technique which was introduced in this paper by Lloyd and collaborators. So you can show that using n copies of state phi k, an unknown state phi k, we can approximately implement this unitary with an error of order 1 over n and time, which is n log d, n times log d, basically. D is, again, the dimension of the Hilbert space. So basically, if using these given copies, we can efficiently implement these boxes. But for now, I'm not going to assume that I have these boxes. OK, so now finally, we are ready to talk about the algorithm itself. So this is basically the circuit that emulates the action of unitary U. So here, I have T ancillary qubits. T is an integer in this integer and is a parameter in this algorithm that determines the accuracy of this task, the accuracy of the emulation. So the ancillary qubits are all initially prepared in a state minus, a state 0, minus 1. And K1 to KT are T integers, T random integers, which are between 1 to capital K. Remember, capital K is the number of distinct input samples. And they are chosen uniformly and independent of each other. Okay? Uniformly at random and independent of each other. That's a very important assumption. And then there's a particular state phi 1 in. That's a state that I choose at the beginning of the algorithm. And its corresponding state phi 1 out. This is just a random state that I choose. And I call it phi 1 in for simplicity. So let's go through the algorithm quickly. So in the first step, I couple my system, which is in this unknown state psi, to a first ancillary qubit using a control reflection with respect to a state phi 1 in. This is my favorite fixed state in the algorithm that I have chosen at the beginning. Then I apply Hadamard on the ancillary qubit. Then I do control reflection with respect to this random state phi input K1. And then I repeat this 3 steps, basically, with different ancillary qubits. Each time, I first apply control reflection with respect to input 1. Then I apply Hadamard. And then I apply input reflection, control reflection with respect to input, a random input, basically. Until the last step, where I apply this control reflection with respect to input 1 and Hadamard, and a control reflection with respect to a random input. And then at the end of this stage 1 of the algorithm, I just throw away my system. I don't care about this state anymore. And I prepare it in a state phi 1 out. Remember, I'm given copies of this state. So now I can use one of these copies and prepare my system in a state phi 1 out. And then in the last stage of the algorithm, I basically undo whatever I have done in the first stage in the reverse order, except instead of reflections with respect to input states, I do reflection with respect to output states. Okay? And then, so for example, in the first step, I do control reflection with respect to output T. then Hadamard, then control reflection with respect to output 1. Then, and in the last step, I'm doing a control reflection with respect to output K1, then Hadamard, and then control reflection with respect to output 1. And then the claim is that if T is sufficiently large, the output of this circuit is approximately U psi. Okay, so let's try to see why this is the case. And to understand this, let's focus on the first block in this algorithm. So in the first block, remember again, I first couple my system in a state psi to, I apply this control reflection with respect to input state phi 1, then Hadamard, and then control reflection with respect to random state K1. So what's happening in this first block? Well, to understand this, let's suppose my state was in a state phi 1 in. It's not in general, but let's suppose this is the case. If my system was in a state phi 1 in, then when it goes through this reflection with respect to phi 1 in, I get a minus sign. And so I have a phase kickback. And the state minus, the ancillary state, the state minus of the ancillary qubit becomes a state plus. And then after Hadamard, it becomes 0, which means that this second random reflection doesn't work. So in other words, if the system was in a state phi 1 in, then it passes through without any changes. It just remains in a state phi 1 in. On the other hand, suppose the system is now in a state which is orthogonal to phi 1 in. In this case, when it goes through the first reflection, nothing happens. The reflection acts like identity. And so a state minus remains minus. And after Hadamard, it becomes 1. And then in this case, you apply this random reflection on the system, control random reflection on the system. So to summarize, what's happening in this state 1 is basically this. You are asking the system, are you in a state phi 1 in or not? If the system says, yes, I'm in a state phi 1 in, you do nothing. If the system says, no, I'm not in a state phi 1 in, you apply a random reflection on the system. And then you keep doing this. You keep doing this with different ancillary qubits. And the claim is, you probably can easily see this, that after repeating this for sufficiently many times, the system is pushed to go to this state phi 1 in. The state phi 1 in that, by the way, you don't know what is the state. But because you are given this copies of this state, you can still do this. You can push the system to go to a state phi 1 in. Why? Because if it's not in phi 1 in, you do another measurement. You're asking the system, are you in state phi 1 in or not? And if it's not, you apply this random reflection. With some probability, it finds some component in direction phi 1 in, and then you absorb that component, and then you keep doing this. Now, this is the intuitive way to think about this, but you can formalize this intuition. And to formalize this intuition, it's useful to think about what's happening from the point of view of the system, the reduced state of the system, when I trace over this ancillary qubit, and when I average over this choice of random integer k. So then you can easily argue that what's happening from the point of view of the system is described by a quantum channel, W, which is basically described this process. First, you do the projection P, which is basically the projected to a state phi 1 in, or to the orthogonal subspace. If you are in the state phi 1 in, the state remains unchanged. If you are in the orthogonal subspace, you apply this random unitary channel D. So the random unitary channel is D is basically the process where you apply one of these random reflections with equal probability. Okay. And now what happens when you apply this process T times? Then using the fact that, again, if you think about what's happening from the point of view of the system, the reduced state of system, using the fact that these ancillary qubits are initially uncorrelated, and using the fact that these random integers are independent of each other, you can argue that the overall effect of this channel on the reduced state of system, when you average over these integers and when you trace over the ancillary qubits, is channel W to power of T acting on psi. So channel W is repeated T times, basically, right, from the point of view of the system. And now you can argue that basically the system, if T is sufficiently large, then the system should be pushed to one of the fixed point of the channel W. And this is where basically the magic happens, or the cool part of the algorithm works. It turns out that the channel W has a unique fixed point inside the subspace, the relevant subspace. And that unique fixed point is just a state phi 1 in, if and only if this condition is satisfied, basically. If the algebra generated by this input states is the full matrix algebra on H in. So this condition guarantees that the channel W has a unique fixed point, and also channel D, this random unitary channel, has a unique fixed point. The unique fixed point of channel D is just totally mixed state inside this H in, and the unique fixed point of channel W is the state phi 1 in. Good. And you can, I mean, this intuition also explains that as you repeat this process T times, the probability that you are not in a state phi 1 in is exponentially small in t, because just the form of channel shows this. Okay, so at the end of this process, after if t is sufficiently large, I can assume that with high probability, I should be in a state phi 1 in, right? With the probability of not being in a state phi 1 in is exponentially small in t. Okay, so for now, let's assume that I am in a state phi 1 in at the end of this stage. So if I'm in a state phi 1 in, it means that the final state of the system at this point is independent of the initial state psi, right? So it's just in a fixed state, which is independent of psi. But now, remember, I talked about quantum channels and measurement, etc., but the entire process is still unitary. And so information should be conserved in a unitary process, which means that information about psi still should be somewhere. And it's not in the system, so it should be in the ancillary qubits. So in other words, by pushing the system in a state phi 1 in, you guarantee that all the information about the state psi is now uploaded to these ancillary qubits, right? So and this immediately implies that, for example, if I just throw away my system and prepare it in a state phi 1 in again, and then undo whatever I have done before, I should get back the state psi. All the information is there. I don't tell you how the information is encoded, but we know that the information is somehow encoded in these ancillary qubits. Now, suppose instead of doing this trivial task, doing the identity, I do a rotated version of this. So basically, I rotate state phi 1 in by u, and conjugate all of these contour reflections by u. So if you rotate phi 1 in by u, you get phi 1 out. And if you conjugate reflection by input state k with u, you get basically reflection with respect to output state k. And so this basically immediately means that if I apply this, if I run this circuit, I prepare the system in a state phi 1 out and do contour reflection with respect to output state. At the output, I should get a state u psi. In other words, I have emulated the action of unitary. I transform the unknown state psi to a state u psi. And the argument that I presented before explains that infidelity, or the probability that the system is 1 minus fidelity with this desired state u psi, should basically scales like it should be exponentially small in t. Good. So I call this method emulating with via coherent erasing, because the idea is that you coherently erase the state of system, you push it to a fixed state, independent of the input state, and in this way you guarantee that all the information is uploaded to this ancillary qubits. How much time do I have?
You didn't see the 5?
Okay. No problem. So okay. So let's skip this. And using this argument, you can show that if you are given this perfect contour reflections with respect to input states and output states, then to achieve an error epsilon, you need choose t, the number of steps, to be something larger than or equal to this. D is the dimension of this relevant subspace. And so the important thing is that t scales logarithmically with the inverse of epsilon. Okay? And also t scales T also scales with the inverse of the spectral gap of this channel D. And so, I mean, this is something that should be expected, because the convergence in this process depends on basically the spectral gap of this channel D and channel W, and that basically determines how fast you converge. And this spectral gap, by the way, can find some information theoretic interpretation, which basically tells you that how much information you can obtain about this the unknown unitary by looking to the sample input and outputs. Good. But in the actual algorithm, I'm not given this ideal contour reflection. I have to simulate the contour reflection using the copies. And it turns out that this is actually the dominant cost of the error here. This is the dominant cost and the main source of the error. In particular, if you simulate each of these contour reflections using the given copies, then it turns out that the sample complexity, the total copies that you need to achieve error epsilon, will scale something like this. It's d squared times epsilon minus 1. Epsilon minus 1, epsilon is again the error, and is divided by the inverse of the square of the gap. Again, the gap is relevant. And then runtime will be just n total, this sample complexity, times log d, the dimension of the Hilbert space. Okay. So the last thing I want to say is a state compression algorithm based on this idea, which is one of the applications of this. So in the version of the algorithm that I presented to you, it's not efficient in terms of the number of qubits, ancillary qubits that I use. And that's basically because if you think about this, and I mean, the reason that I chose this to present, I mean, it's because it's easier to understand, but it's not necessarily the most efficient one. It's actually exponentially bad in terms of the number of qubits. And the reason is that basically, if you look at this circuit carefully, you understand that information is actually information about the state psi encoded in these ancillary qubits using a unary encoding. And if you basically do a binary encoding of this information, you can achieve the same task. You can achieve basically the same precision with a logarithmic number of qubits, log t ancillary qubits. And then in this way, basically, you can think of this as a compression algorithm. So you start with a psi, which lives in a large Hilbert space, capital D dimensional Hilbert space. But you know that it's restricted to a random d-dimensional subspace in lowercase d dimensional subspace in this large Hilbert space. And then using this technique, if you are given this sample that stays in this random subspace, you can compress your state to a number of qubits, which is log lowercase d. So basically, you can compress almost optimally using this approach. Good. So my time is over, so let me just summarize. We saw that using this algorithm, universal quantum emulator, you can achieve emulation with runtime, which is scales like log d, like where capital D is the dimension of Hilbert space, and times poly d, where lowercase d is just the dimension of this relevant subspace, and sample complexity is just independent of the dimension of Hilbert space. Thank you for your attention.
Questions? Yes.
Hi. Nice algorithm. I was wondering, here you consider, okay, if your input states is correlated with some other system, does the correlation are preserved or some?
Yeah.
Okay.
Yeah. Well, I mean, you can argue that this channel, I mean, as a channel that you implement is close to the channel corresponding to unitary U.
Okay, so you can compare channel.
Yeah.
That's
Yes.
Okay. Thank you very much.
More questions? Yes.
A question about the spectral gap of the channel. For a fixed set of input states, does this gap depend on the unitary that you're trying to emulate?
No, it just depends on the relation between these states. So for example, see if I started with this example, you start with the state 0 and 1, in which case it's impossible. But what happens if it's not exactly state 0 and 1, but let's say they are almost orthogonal, you know? They're close to a pair of orthogonal states. So their inner product is very small. Then you can argue that this spectral gap, so you should pay for that somewhere because the information that you obtain will be very small. Information that you obtain about this unknown angle theta will be very small. So you should pay for that at some point, and this is exactly the point that you are paying for that bad choice of input states.
Thanks.
More questions? Maybe I can ask a silly question. I mean, suppose you're not allowed to basically get access to this, to this full U. Suppose you can only basically sort of make measurements on the output state. I mean, is it possible to do basically better than tomography?
You can argue that basically you cannot do much better than tomography because emulation in a way, well, think about this task. I start with a state 0, all qubits in a state 0, and my unitary bring it to an unknown state psi. Okay? So to emulate this unitary is equivalent to being able to prepare the state psi. Right? So the complexity, so I should obtain all that information about the state.
But suppose I'm asking you to maybe reproduce the measurements on the state psi only, say, in one basis.
Oh, I see.
Something
Yeah,
like that.
That's a different question. I think that actually relates more to the question, the talks that we had yesterday, like Scott Armstrong's work or Leah Smolin and David Gassett's work. Sorry, Gianna Smolin and David Gassett's work. Yeah.
Okay. Any more questions? Okay, let's thank Iman again and go for lunch.